chemical bond holds the molecule together while intermolecular holds the parts together.
What type of parts?
The electrons.
Reverse.
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 Alright. So, okay, hang on. Then you can focus on me if y'all are talking around her. Alright, so a chemical bond holds the atom together. Intermolecular force, not atom, holds the molecule together. So intermolecular forces holds what together then? Don't ask me this in stuff.
Like the protons, neutrons, and
No.
electrons.
No. Alright, Quentin.
Intermolecular forces hold the elements together.
Anyway.
Closer, yes, I'll take that. So it has to do with the idea of a chemical bond holds, like for example, water. Water
Oh, I know it.
is. Alright, what type of bond is this?
Chemical.
Okay, it's
Water.
What type? What type? Because remember, there's covalent and metallic. Which one is it, Ethan?
Covalent.
It is covalent. So this is a type of chemical bond. Pay attention, gentlemen. This is a type of chemical bond. So, but remember, water sticks to other water molecules as where? We talked about this, I think on Friday very loosely. We call that cohesion, where those molecules of the same type stick together. And so because of that, there's intermolecular forces that make one water molecule stick to another water molecule. We haven't quite talked about all three of them yet, so I won't ask which one holds it together. Alright, do you just know it's for fun?
Huh?
Do you know it's for fun?
What?
Never mind.
No, I'll answer the next one.
Alright, number 2, explain the dipole-dipole force. Alright, Chris, go for it.
The dipole-dipole forces are the forces between polar molecules.
Good job. So a polar molecule is a what?
Huh?
A polar molecule is a what?
Anyway.
Molecule that has empty spaces. It's not the same all the way around.
Okay, so it has partial positive and partial negative? Good job. Number
I have
3,
a question.
what causes London forces, Ethan? London forces, Ethan.
London forces are caused by the dispersion forces.
The what?
Dispersion forces.
Okay, of the what is being dispersed or what is shifting and moving around?
Electron.
There you go. Number 4,
That's not what I
explain the difference between a hydrogen bond and a dipole-dipole force. So it's
I'll do
hydrogen
it.
bond, it sounds like a chemical bond, it's
I'll do
not,
it.
it's another name.
I'll do it.
But it's Quentin's turn. Alright, Quentin.
Dipole forces work when it's the same molecules together, while hydrogen forces work when there are different space molecules.
Not quite. Alright, Ethan, what you got?
Hydrogen bonds is, I didn't hear what you said. Hydrogen bond is unusually strong intermolecular force between molecules containing hydrogen, unlike dipole-dipole force.
Go, sir. Alright, what you got, Chris?
Hydrogen bonds are stronger.
They're what?
Hydrogen bonds are stronger.
Alright, you said that already.
That's all I have.
Alright, so explain the difference between them. So a hydrogen bond, did you catch what type of atom hydrogen has to be bonded to make it have that extremely strong charge?
Hydrogen.
Hydrogen has to be bonded to who? So the hydrogen.
Oxygen.
Good job. Oxygen, nitrogen, and fluorine. So we'll talk about how that works later on for it, but yes, it is those three. And they are much stronger than a regular dipole-dipole force. Alright, so Jamie has decided, I think part of it got cut off at the beginning for it, but make sure you email in the lab report sheet to me as well. I already collected all the gentlemen's here in class, so make sure you email it to me. Alright, you can go ahead and get out, be spiritually write down stuff.
You don't know.
No, you'll be ready.
Have you watched The Grinch this year?
What?
Have you watched The Grinch already?
This
I
year,
have.
no.
I've watched it.
Like, you know the scene from The Grinch though, where the Grinch has like the book.
This doesn't feel like it's related to chemistry very much.
It does, because it's something Ethan just did. You know when he shaves and his face is all cut up, so he puts the bag over his head, he puts his feet up, he puts the book up and everything? That's what Ethan just did with his notebook, and it reminded me of that, so I figured I would ask if you watched The Grinch yet.
It's a very long graphic.
Ah!
Okay. Alright, let's go back a little bit as well. Make sure you're not too loud. So
Why do you call us
earbuds.
gentlemen if
No,
we have the IQ of 4-year-olds?
because I'm nice.
Y'all have done.
Alright, thinking back
It's
over
strong.
it, it's been a while. So thinking back over it, what is a type of chemical bond that's between metals? We will start with
My
this.
turn.
Okay.
Metallic.
Now, not girl. Don't
My nose
shit.
is on
Oh, hang on.
fire
Sorry.
right now.
Alright, can I throw my phone actually?
No. Although it's in your pocket, I'm about to take it.
No, use the
Remember,
blue
it should
ones.
be-
Remember that time in
It's not on
remember that time in Spanish? That's my calculator.
It
That was
was
history.
in history.
Because like that's my calculator. It shows like Then let me sit. He was like, here's my phone.
I'm gonna
Just
try
take
to
it.
hear
Take my soul and my life if you could, please.
Alright, what is the type of chemical bond that is between metals and nonmetals? You didn't answer the question! Good job.
Please
I
take
don't
it.
say you
I
got
like
that wrong.
You're very sad.
I look very fat in that shirt for some reason.
I'm sorry.
I feel that.
Ow.
Oh,
That's why you
What
wear
type
it.
of bond is it between nonmetals and nonmetals? Covalent.
Nice. That was a nice one too. That was a nice little.
Little one over here. getting nice. Ah, you got nothing.
Alright,
No,
what
that's
type of
easy.
bond is characterized by the sharing of electrons?
Ionic?
Final answer?
Yeah.
No. First, let us go down the line. So
Okay, covalent.
Covalent, remember, because nonmetals want them, they share them.
Don't miss.
Let's go! Is that 19?
Alright.
If you beat Quinn, I will give you.
That's over a 19. But look, it's predominantly on 19.
That's on the
Quinn,
line.
is your name short for
That's
Quintavious?
predominantly on
It
19.
is predominantly.
Okay.
Alright, what type of bond is characterized by delocalized electrons? Because nobody wants it.
Metallic.
Metallic.
Nani?
Not me. Not me.
Nani?
Whoa!
Whoa,
Watch
whoa,
out,
whoa, 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 whoa. Hold
Alright.
up. Wait a minute, something ain't right.
Alright,
touches on it.
what do we call the situation whenever you have the electrons are shared by more than two atoms?
What's that one?
D.
Huh?
D.
D? Delocalization?
Delocalization. Good job. The
Holy
delocalized
guess.
electron
Holy guess.
is delocalization.
Holy guess.
Yes?
Alright, it's right here, right? This
No, it's not.
Yeah,
It's
There
right
it
here.
is.
Hold on.
No, it's not.
Yeah. it's
What?
right
Okay.
Last
Let's
lecture
say
was
it's
not
this
there.
line. So
Well, I was
everyone-
not behind there.
I know. This typical guy picked that line. Do not do that again.
This man hit the corner.
Go get it. Be careful. Watch out for Ted.
Don't break Ted.
Don't break Ted's spine.
Don't break him, Chris. You have to buy
Pressure.
Break him.
Did I just see what I just saw?
How do we know
Are
he's
you
a male?
being appropriate?
How do we know he's
Yeah,
a male?
Chris,
This man might be inappropriate.
You have to
Put
move
Ted's
Ted.
back.
You have to move Ted.
That just pinched me. That hurt really bad.
Don't break Ted. Don't break him.
He's really nice teeth, Dad.
He does.
White.
Must have had
Let's get the
braces.
water all
He's
over.
been using that Colgate whitening strip.
I might not actually use it.
Alright.
He's the
What
one.
is, alright, we went over the shapes on Friday, so what is this type of shape?
Really hurt.
What's the third one?
T.
Tetrahedral.
Tetrahedral, so it's a 4. Oh, Jamie can't see it. Oh, I'm too short. I'm gonna pull this down a little bit.
Tommy, Tommy.
Tetrahedral, Jamie! Put it over here so I don't remember.
I'm sorry, Jamie.
That was about to hit 22, 25.
Ooh,
That's like in the middle of all three.
Alright.
No, it's not.
What is this type of shape?
Angular.
Good job.
Another 19.
Try to pop it over there for you, Jamie.
I'm the best.
Quit.
I'm the best player on the basketball team by far.
Quit!
Alright, what is the name for this type of shape? Oh, I'm short.
Start with an A. Where's it start with?
Okay, so it's fatigue because there's 3 atoms.
Trigonal plane here.
Good job.
Why are you
This
doing
worked
that?
last time.
Kobe.
That's a bummer.
The fact that they crossed each other
Yeah.
perfectly looked kind of cool.
Alright, what is this one?
Right here.
Good job.
You can't lie, that looked kind of cool.
You did.
I'm gonna stick right here.
Yeah, it's the.
Turn to Frankenstein. Has anyone ever hit
I
Ted?
hit 14.
Is anyone ever what?
Hit Ted?
Yes.
Yeah.
Did they stop playing?
Yeah, we stopped immediately because I can't injure Ted.
Well, like, could it actually break his skull?
Depending on how y'all throw, I think it
Probably.
might.
Yeah, we might be able
It
to.
really might actually
Has
hurt.
anyone ever hit the ceiling?
Yeah.
You did.
How?
Yeah.
It had to be
Did
on
you
purpose.
hit
It
It
had to be on
really,
purpose.
no, they threw a big arch and it went crunk, but it fell.
Did you hit ceiling, Chris?
No, I haven't.
Alright,
Has
what
anyone
is
ever-
this
has
one
anyone ever-
shape?
Has anyone ever hit Polk?
Anyone here?
Polk.
Oh, yeah.
Poor Polk.
Does anybody
Look at
get-
that guy right there. He is stunning.
That's Fillmore, isn't it?
He looks
I
so
think
young.
so. Alright,
No, that's your Henry.
which one?
What's over?
It's sort of fatigue because there's 3
He has
atoms
mine
that
here.
are reason to delocalize electrons.
Has anyone ever hit Abraham Lincoln?
Not that far down.
That's horrible.
He's like,
Is it 2 words?
Yep, because remember, it's three electrons bonded to a central one. Not an electron, usually electrons, 3 atoms bonded to a central one, and there's a region of delocalized electrons.
Let's say 1 word start with.
Okay, it starts with P.
What's the first one start with?
T.
Oh.
I'm gonna go crazy.
This is why we're not having a quiz on this today.
Huh?
First word.
Okay, what means 3?
Try.
Okay, what word starts with try?
Try.
You're combining.
Triangular.
Can I go, please?
What?
I don't know.
It is your, okay, we'll jump.
Try going up here and be
Try
drunk.
going up here.
Yeah. Can we talk about how Abraham Lincoln has the absolute bruh face right now? He said bruh.
A little bit.
Bruh.
Why you got me hanging up here with these bums?
Look at the with the roof.
I thought
Look
it
at
was
it.
Alright, Ethan's turn. Alright, Ethan. So, is this one typically polar or non-polar or both?
So that one is trigonal, linear, or angular. Trigonal.
Wait,
The one he just did.
Does it make this metal like magnetized now?
If we do it enough, if it's broken enough, it would, but just hanging them on like that won't.
It's normally
Because remember, it has a region of delocalized electrons. So typically, which one is it?
polar.
Polar. This one's almost always polar. Now, what shape is this? Because you didn't know.
Trigonal.
Smooth boy.
What's the second one start with?
P, because it's in 3D.
Playoff P.
Trigonal.
Other one.
Not you didn't remember. I can't remember.
Alright, pyramidal.
It's all fun and games till playoff P comes out to play. Playoff P, which is a basketball joke.
Yeah. Wait. What the world?
Yeah, I don't know what that is.
Alright, this one. It has 2 regions of delocalization. Typically polar or non-polar or both.
Retarded butterfly.
What start with?
Polar, non-polar, or both.
Polar.
Typically it's polar. Most of the time, if they delocalize electrons, they're going to be polar.
You got this. Quintavious, Quantavious.
Corn is a beat.
Nah, bro, I got you.
Ooh.
That's right in the
Okay,
middle.
13 for non-being 13, but 12 and 5's on the line.
I'll read her.
Don't get too much.
Might as well keep it on there.
No, I'm redrawing.
Good job.
I think
Alright.
Pointing throws so
So,
smooth.
polar, non-polar, or can be both?
non-void. No, can be both actually.
Can be both, actually. Depends on what elements are bonded to it.
Did you copy my words? I think can be both actually. You said can be both actually.
Probably. Just
Can
don't
be both.
figure out once you be ready for it.
It's not magnetized.
It takes a while. You have to figure it out, like, but also depends on what type of substance it is, because aluminum can't be magnetized. She made it.
That's so.
That's all.
That's all, y'all.
We're up.
Okay, be careful. Don't do that.
I kinda actually got close.
Alright, so, this one. Polar, non-polar, or can be both? It can be both, depending on what's bonded to it.
Quinn over here.
So,
You might actually beat me, real.
Quan, sound
I like that. You might beat me.
I don't
Hang on,
trust
let Chris go sit down.
I don't trust
I wouldn't trust him either. So let's sit down.
Nani?
Honey.
Sugoi, sugoi.
Good.
It's gonna fall off.
Oh.
Hey, okay.
Hold on.
That's all. That's all.
You touched it, so it doesn't
It's
count. Alright, polar, non-polar,
Now
can be
try
both.
hitting Quentin.
Yeah.
Polar.
Let's actually say it.
Both.
It can be both.
You spit everywhere.
He always says that.
It's like
Okay, don't do that because of Corona.
what's the zebra from Madagascar?
That's right in
That's
the middle.
What is the
I
zebra
think that's
from
really on
Madagascar?
15.
So maybe you can always have yours just for not
Alright.
50.
Quentin, what is the zebra's name from Madagascar?
Maurice.
Maurice.
No.
How do you know that?
Alright, you know when he's like,
No, it's Marty. It's
Yeah,
Marty.
my turn. It's my time because I don't have time to keep going. Alright, so is this one almost always polar or non-polar or both?
not polar. Both.
Both. Typically though, this one's polar because the odds of it being the same element are pretty slim.
Kobe.
Whoa.
Hey, good job.
It's not
Hope that
fall.
won't fall.
Ball.
Alright,
That's 35.
That's,
yeah, that is
that's
35
it.
Good job.
I'm so good at this.
Alright,
No one knows the wings all the way back here.
alright, what do we call, we talked about this on Thursday, but it has been a while. What do you call the forces that hold the molecules together?
Let's start.
What do you call the force that, that's disgusting.
What did he do?
He put his hand in his
No, I didn't.
No, I didn't. You put it in my mouth.
You just put like everywhere else next to your mouth.
That's
Alright,
nasty.
so what do you call the forces that hold the molecules together? They're in between the different molecules.
Let's start.
Intermolecular force.
When you said I would like to think about I want to die.
That's not where I thought it was going. Anyway. Oops.
How are
This
you?
is why Ted's way over there.
Alright, so good, so bad.
18.
Alright, Quentin's turn. Alright, Quentin, we
That's
barely
good
got into
practice.
these, so it's okay if you don't remember them too much. But
Give me a basketball.
what is the weakest intermolecular force?
Please start with.
It starts with a L.
Oh, yeah.
It's named after the guy in the city.
Wait, what?
Louis? I don't know.
Yep.
London forces.
London
Oh.
force. It's the weakest force.
Look at it, look at it, look at it, look at it. Go.
Alright, what force is between all
Isn't
molecules?
it technically my turn? Technically, because it was just his and then I stole.
No.
It starts with a D.
Don't because of COVID.
It starts with a D.
It starts with an L.
L. What?
Elmer starts with L too?
If it's
Oh,
between
London.
all forces. Yep. This one is the only one that's
Okay.
between all
What
forces.
is the city?
I
in
thought
England?
so. No,
It's
it's
London.
That's what I was thinking for.
Garbage can. Trash.
Trash.
We said the same time.
Alright. What is the name for the force that's between polar molecules?
Please start with.
D. Dipole.
It's like a Pokemon, a really retarded Pokemon. Ditto. It's like Ditto. If Ditto was actually useful.
Ditto is the most useful stuff about.
Actually, Ditto.
Don't even.
Ditto, if you put it in a breeding thing there in Pokemon, it can breed any Pokemon, even legendaries.
Not
Anyway.
bad. Alright, that is much that I have time for right now. We have time to get the end some more. Alright, who's got, y'all got some high rollers, so who
We have
got
to see.
30 or more?
Let
Some
me
of y'all
add.
got some high points. Alright, how many of you have 50 or more?
Let me add.
Hurry, Ethan.
Yeah, I'd say that too.
Because we don't know.
I only got 51, so I probably lost.
Yeah.
Alright, who's got 60 or more? 70 or more? 80 or more? 90 or more? 100 or more? Alright, how many do you have, Quentin?
115.
Alright, how many do you have?
7.
Alright, so don't forget your candy.
You're
I
what,
have
7?
Christmas chocolate now. Alright, turn it over. So, anyone have any questions though about the shapes and how to tell? Oh, almost forgot that name. Anyone have any questions about the shapes and how to tell what shape is what? And if you're given the Lewis structure, how to tell what shape is what? Your quiz over that is tomorrow, so letting you know now. So again, most of you did, I'm gonna grade on your labs today, and we'll go over it tomorrow in class. That way, so if you're confused on something, you can ask, well, there goes that molecule. You can ask me tomorrow about it to make sure, but if you're stuck, or if you don't know what's going on, you need to ask me there tomorrow to figure out, okay, how much tell what shape it is. Does anyone have any questions about, that they know right now, that they're stuck? Okay,
I'm always stuck.
no, we'll study tonight, you can, and then ask me tomorrow, or ask me later on today,
Stuck
so
in a
don't,
realm of sadness and depression that I can never escape.
don't
The inner
distract my
sadness.
class, don't drag out my
What
class.
was he
Alright.
doing?
So, we left off talking about intermolecular forces. What are intermolecular forces, Chris?
Forces that hold the elements together. The element together.
Describe it.
I can't describe it.
Alright, so,
Like
is
London
it
forces?
like where it holds hydrogen to oxygen, or is it like where it holds all the water molecules to other water
All the
molecules?
water molecules to the water molecules.
Good job, that is the correct answer, but I wanted to make sure. Typically we say molecules because you can have intermolecular forces between the same atoms, like oxygen will stick to oxygen, but it's not nearly as common as a molecule to another molecule. That's the reason why they're called intermolecular forces, because they're in between the molecules. Alright, this is an example of what?
This is extremely over exaggerated.
Yes.
This like some kid that had too much fun in a camera class.
Okay, well keep in mind, what type of force does this demonstrate?
Dipole. No, intermolecular.
Which type?
London force.
London. Alright, when do you have a question for
Do I have
Trey?
freebie?
What?
Do I have freebie?
You do this class? Let me check.
I hope so.
I feel like you haven't used it yet, but I don't know. I always get this quarter and the first quarter mixed up. That's how much lunch has. You do have your food. Goodbye. Alright, so this is with London forces. Alright, so it's showing you with the London forces what is shifting, what is moving around. Ethan.
Electrons.
Electrons. Now keep in mind, what is this little lowercase g looking thing? What is that first off?
Lowercase delta.
It is lowercase delta. What does this mean? Why is there a positive and a negative? Chris, what you have to turn?
Because it's a non-polar or a polar element.
Okay, so it's polar right now. Why?
Because it's not the same all the way around.
Okay, because what's shifting and what's moving?
Then I don't know.
Alright, so London forces are caused by what?
No, not dipoles. The instantaneous.
Alright, make sure you're not getting distracted.
I
So
wasn't
yes, it's
getting
the electrons moving each other around. So keep in mind, these aren't locked in. So because we call this a polar molecule, because it's the electrons that are shifting and moving around, and they're moving so quick that it'll do this thousands of times in a second. So it's really, really fast. So they're showing you a slowed down version. This idea if it's moving. You have a question, Chris?
I was saying, they're so fast.
They are. Now keep in mind, I keep hearing a lot of comments over there, Chris and Ethan. So make sure you raise your hand if you have questions. I don't have time to just be stopping over and over and over again. So do you have a question about this? Alright, so the next one your book talks about is the dipole force. What's a dipole force, Ethan? I got pictures.
It's a dipole force.
Which is dipole force is a dipole force. So what is a better
They're
explanation?
not as strong as iron.
They're what?
They're not as strong as iron.
You're right, they're not. So if you had to describe dipole force, what is it, Chris?
Oh, I got it. I know.
Alright, what is it?
The force between neighboring polar molecules due
What
to
page are you
attraction
on?
oppositely charged in 140.
Good job.
You're
So,
welcome,
keep in mind for this one, that should be inappropriate.
I'm sorry.
Be inappropriate.
I'm sorry.
We talked about
I know, I didn't mean to.
Alright, so this is a dipole force. So this one has a permanent positive and a permanent negative in. So that's the difference between a regular London force and a dipole
Did they all
force.
look like this?
What?
Did they all look like this?
Not that particular one. Your book has this one as an example. It's the bottom of page 140. It's the acetonitrate one. So that's how come it has the different ones. But keep in mind, if you were to have a polar molecule, like for example,
Oxygen. O2, H2O.
because this one has hydrogen bonds on the inside, because it's hydrogen bonded to it. So which one would just be a pure dipole?
Fluoride carbonate.
Yeah, that would work. So it'd be like this. No, it wouldn't. Because why is this not dipole?
It's hydrogen.
It doesn't need 4.
I'm in London.
Okay, so why does carbon need 4 though?
Because it only starts out with 4.
So it has to have 4 bonds, so what shape would this be?
It's my question, Ethan.
Tetrahedral. Alright, but why is it not dipole?
I don't
It's a
know,
wonder.
I'm rudely interrupted by this
Okay,
heathen.
be nice. Okay, so, but yes, you did interrupt. Okay, so why is this not dipole?
It's not polar.
Good job. Alright, we'll just cheat and we'll just change one. We'll say this one's hydrogen. Alright.
That's not polar either. Oh yeah, it is. Never mind.
Yeah, now it would. Okay, because all of these would be what?
What do you mean?
Like fluorine, and fluorine, they would all be what?
Positive. No, negative.
Negative. Hydrogen would be partially positive. So okay, this would be a polar molecule. So this one would have dipole forces because it would try to orient itself so that way it's positive to negative. Kind of like with magnets.
Is London forces always are London forces the same thing as that, just for like non-polar?
Well this one, keep in mind that the electrons are locked in and they're permanently shifted. Well, London force electrons are moving constantly because do you remember what's the principle that says you can't know their position and momentum at the same time?
Is it the Hundred rule? Aufbau? No, uncertainty principle.
Good job. And so because of that, it's one of those, London force happens over and over again because the electrons, they're constantly shifting, constantly moving, so it generates it. in split seconds. Well, this one is more of a permanent thing, so they're kind of always there. Okay.
Do we have more than one day of review for this exam?
Yes. Yes, we do.
Like one full day?
Yes.
Thank
I
you.
plan for, but well, keep in mind, it's from the beginning of the year
Yeah.
until now, and so I plan on spending about 3 days loosely, give or take. So that way we can go over all
Yeah,
the
for
math.
history.
Because remember, you have things like balancing equations,
I love that.
History.
you have molarity, you have the state changes.
Are we
and
the
what-
longest? Are we the class that you review with the longest?
It depends on when the exam falls, and I don't know till last week when the exam falls. So I plan on the idea that every exam happens on the first day, but every exam
When
does
is
not
our- when
happen.
is
Do we
our
have
exam?
chapter 10
You will
left?
find out. What?
Or is chapter 10 over?
Yeah, we're about to be done. So if you look at the book, you realize, wow, we're
Nine?
about to be finished. Yeah, we're about to be
We're
finished.
finishing 9, that's the last one.
That's it. We're done. Yeah.
We have like a week and a half left.
Yeah, I know.
What are we gonna do?
You'll find out
Week of review.
a little bit. Well, just
We're gonna have a
stuff.
crap ton of quizzes.
Okay, not in my class.
Is that?
Not in my class.
We're gonna have a ton of quizzes.
No.
You too?
Alright,
We're
ready to
gonna
go?
have- we're gonna have a lot
Alright,
of-
so this is Dipole Force, so let's make a note for this one as well. Alright, the last one we haven't talked about yet is on page 141. So this one has, oh, I almost skipped over that common help. Alright, so if I have a larger atom that has more electrons, will its London forces be stronger or weaker? Quentin? Stronger, because there's more electrons as they get disoriented. Alright, so hydrogen bonds is the last one you were talking about. Now it has the word hydrogen bond in it because it's so strong. It is technically not a type of chemical bond, because what are the 3 types of chemical bonds, Quentin? Good job. So this one is called hydrogen bond, but it sounds a little misleading because technically it's not a chemical bond, but it so strongly connects the one type of molecule to another type of molecule. Because if you have a hydrogen bonded to fluorine, nitrogen, or oxygen, make a note of those 3 up on page 141. It has to be those 3. Now keep in mind, fluorine is the strongest what property?
Electronegativity?
Electronegative. And so because of that, it wants them the most. And so it's these up here, the smallest ones, and the ones closest to fluorine. Nitrogen, oxygen, and fluorine. Not fluorine, so make a note of the 3 at the top looking across for it. So it's nitrogen, oxygen, and fluorine. Because they're so small and they want it so bad, that's what comes there the strongest. So it has to be hydrogen to nitrogen, oxygen, and fluorine. What if it's what if it's hydrogen to arsenic? Will it have a hydrogen bond? No, it has to be hydrogen to nitrogen, oxygen, or fluorine. It has to be those 3 for it. This makes them incredibly strong for it. I don't think I showed the moving molecules on it. I think I pulled it up and then I don't think I actually pushed
That's
play.
okay.
No, for this one, Dipole forces. So it's showing you for this one how strong they are, that they try to orient themselves positive and negative in. And so like those forces. Did I? Let's see if we can watch it again.
Wow.
So this idea they orient themselves for it.
That's me when I draw.
Nah, me too.
Look at the house.
Yeah, a little bit over exaggerated, but it's just showing you. Okay, back to this. Alright, so it has to be hydrogen bonded to oxygen, nitrogen, or fluorine. It makes them incredibly strong because oxygen, nitrogen, and fluorine pull the electrons so close to it that this develops a much stronger partial positive and a much stronger partial negative. Now it's still not ionic because it didn't take it away, but it's the idea of they're sharing technically, but that's the reason why they're so much stronger. Okay.
Is that how they make hydrogen bombs?
It's a little bit different for it. That has to do with the idea, it's a little bit different. We'll talk more about what's happening with
Like, do they use
fusion.
hydrogen bonds?
What?
Do they use hydrogen bonds?
But it's because they use hydrogen as kind of like, I think they use it like a starter, that's why it's called that for it. Alright, we'll talk more about that. I think that's in chapter 18, I think is in nuclear chemistry. So we'll get
It's like at the end of the year.
It's very close to the end of the year. Alright, so oxygen and hydrogen, make a note for this one. I'm trying to think.
It's literally the last chapter.
Yeah. Alright, so the usually strong electric forces between molecules containing hydrogen may bond to a highly electronegative element is a hydrogen bond. We draw them as dotted lines to represent, because again, it's not a full-on chemical bond, so that's the reason why we use it. Now, your book points out these hydrogen bonds tend to typically be much stronger than a regular molecular force. So keep in mind, which one is the weakest in a molecular force? London, so this one is the strongest. So make a note for this one, you wrote that as your homework, make sure that yes, it is the strongest one for it. Alright, this is one reason why water has such strong properties, and that's one reason why water forms up certain shapes as it freezes. Does anyone know what shape loosely, that snowflakes and other particles form up whenever they freeze.
Octagon.
Not an octagon, you're close.
Hexagon. Heptagon.
None again.
You said it, so hexagon are six-sided shapes. That's the reason why we draw them as six sides, is because it forms that shape, and they think it's part of these molecular forces. Alright, we're gonna watch a quickish video about ice and water. I think some of you saw this in physical science last year or 2 years ago, I don't care. I
Is
just
it over
wanna make
4
exaggerated?
years ago.
Yeah. What?
Is it over exaggerated?
Not really, it's just a little bit dated. It's getting a little bit older now.
That
I mean, it still works.
Just like my soul.
They don't do physical science in 8th grade, do they?
Ninth grade. You get life science in 7th and 8th grade.
Life science.
Jamie, I'm not sure how well it'll show up, I'm sorry.
Produced.
I asked you to not do that previously. Let's not do that. Try somebody just.
And that just made me want to die. That was so scary.
Alright,
Ooh, I marked it where it was.
I'd rather watch Halloween.
The creators were
Okay.
Can you do something again?
So, for this one, again, this one has a bunch of, oh no, we're not watching the whole thing, there's so much stuff. So I think we watched bits and pieces of it. This one is only about 5 minutes section of it, we're talking about ice and water and snow in particular.
Oh, yeah.
Yeah, I can't remember some more people
I'm
in the
never
list.
watching this.
Okay,
We have like that week and a half off. Can we watch something?
I plan on watching something else actually.
That's what we're doing.
Charlie Brown Thanksgiving.
Alright, go good luck, good luck.
Thanksgiving is
works declare his wisdom.
I don't know how long it'll show up, Jamie, I'm sorry. Remember done talking during the video? No.
Thousands of years ago, God asked Job, "Have you entered the treasury of snow?" Now, no man living at that time could have known fully about the treasures of the snow. But with the advent of the microscope, these elaborate crystals can now be wholly appreciated. These are actual snow crystals that have reached Earth intact. Snow crystals form in the clouds where water vapor condenses and crystallizes into ice. As the crystals grow, these remarkable patterns emerge. Complex, symmetrical, and beautiful. They are breathtaking to behold. In contrast, man-made snow has none of the elaborate structure found in snow crystals.
Snow crystals are made out of amazing water molecules. Each oxygen atom has a little bit of negative charge, and it holds on to 2 hydrogen atoms that have a little positive charge, and it holds them 104.5 degrees apart. When you reach the freezing point, suddenly they reach a point where the electrical attraction of plus and minus charges can pull them together. That's the energy source. And then that shape God gave the water molecules, they line up to form those beautiful crystals, each one unique, each one a reflection of God's creativity.
Every day, trillions of God's transparent treasures fall to earth for our discovery and joy. And yet, no two are exactly alike.
I believe that God built this hexagonal shape into the individual water molecule because of the way they have to fit together. They form this hexagonal shape as they add on molecules and grow outward. And each individual ice crystal is made up of literally millions of water molecules, and although they fit together in a particular way, as they grow outward, the ice crystals falling down through the cloud at different temperatures, they begin to get different shapes. So every ice crystal is going to be slightly different than every other one.
Each crystal is built on a hexagonal pattern and exhibits a marvelous symmetry of design. Truly, there is a treasury of snow, just as God declared 4,000 years ago.
There's 2 things about ice crystals that just really excite me. One is literally the beauty. You look at them and you see all these patterns with these flat faces and the structure that's there. There's over 100 different basic types of ice crystals. It's just the beauty of it. And that tells me something about God. It tells me that God loves beauty, and He loves me because He provided this beauty to look at. So it resonates with me. The other is the way in which the ice crystals are ordered, the way in which the individual molecules fit together. That fits a particular consistent pattern time and time again, tells me that God has designed it.
There is also a spiritual application. As each snow crystal is distinctly patterned, so each human, each soul is unique and of special concern to our Lord. As God's creative hand forms ice crystals with loving care, so too he intends to form each person to reflect his glory. Compared to the rest of creation, snow crystals are simple, yet the great architect's attention, even to the countless snow crystals he forms each day, is an unmistakable mark of his care.
God has built into not only ice crystals, all kinds of other molecules, all kinds of systems, relationships, and processes that we don't even begin to fathom yet today. That's one of the reasons I'm a scientist. I love trying to find out how things function, how they operate, and apply mathematical equations to them, because I feel like I'm touching the face of God, if you wish.
Alright,
I
so
wanna
again,
be-
really quick for it.
I
Alright,
wanna
wait,
be-
you're okay. Yes,
I want to be as happy as that first guy was when he was talking about when he was talking about the snow molecules.
Mhm.
So,
He's
yeah,
very-
I want to be as happy as him when I'm at my job.
Yeah, that's one reason on why you want to pick a job that you actually like. And that's one of the reasons why I teach science, is because I don't want to do the same thing every day in like a science lab. But if you're a science teacher, you get to talk about a whole bunch of different stuff, a whole different applications. So find something that you like and that you're good at, and that makes money. You got to eat.
Would you ever
And then-
teach like English?
I can, because I was good at it in
You
high
don't- you
school.
like it?
It's been a while. What?
Like, what's your least favorite subject?
I don't know.
English is my
actually.
favorite.
I was not very good at Spanish.
Spanish
so I
is
think
my least
Spanish is
favorite.
probably my least favorite, but I mean, I did well in all of them. I had to work the hardest at that one. Okay. Alright, so anyone have any questions though about the 3 different types of intermolecular forces before we move on? Alright, so the next major thing is with crystals, and we're talking about solids in particular for. Now, you might remember this from physical science last year, that there are 2 major categories of solids. So, thinking about the states of matter, okay, what are the 3 common states of matter? Okay, Chris.
Solid, liquid, gas.
You're done to what's the 4th one?
Proton. No, not proton. Starts with a P,
It
right?
does repeat. It's in stars.
It's in stars.
Stars.
I know this too.
You do. It's okay. It's just been a while. This is one reason why we spent a couple days reviewing for the exam.
It's on the tip of my tongue. It starts with a P. What's the next letter?
L.
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 Plasma.
Plasma. So those are the 4 states of matter, 3 common states of matter on Earth. So for this one, we're talking about solids in particular. So kind of going back again for it. So think in mind about the 3 common states of matter. Which one has the least kinetic energy? I know this has been a while, but your exam is coming up.
Solid.
Solid. So this is why they are locked into place for it. There are 2 basic types of solid. You have crystalline solid, which are locked into an ordered pattern. And then there is amorphous solid, where they don't have an ordered pattern for it. So amorphous solid, these are examples like tar, butter, grease, glass, some plastics. They don't have a specific melting point. They start to basically melt over a wide range of temperatures altogether. How many of you have seen glass blowing or glass shaking before?
We did
Okay,
it in here.
what?
We did it in
Oh
here.
yeah, we did. So that's the idea. Basically glass, it doesn't all just melt at once, or it's not like ice where it all starts to liquefy. It becomes basically more and more pliable until eventually it turns into the liquid. So that's the idea of amorphous solids. They're not locked in, and they'll gradually melt or start to become more plasticity, if you think of it that way, over a wider range of temperatures. They don't full on just melt like ice. Okay.
If melting glass touches your hand, it like burns the skin off like completely, right?
I don't know if it would burn. It would hurt.
Would it become solid on your finger and it'd be like stuck to your skin?
It's quite possible. I have never tested this, and I have not looked it up because I did
You've
not
never
want.
tested
I
it?
said I did not want to test it. I don't know if it would melt your skin up. It'd be very hot because remember how hot we took it out of the burner. I believe it's around 300 to 400 degrees whenever it starts to do that. Would it melt your skin off? No, but you definitely have gotten burned, probably a 2nd degree
How
burn.
does it have to be to melt your skin off? Like 1,000?
I'm not sure. It probably depends on what touches you.
I know
or
you can get burns if you're even like 5 feet away from lava. You can get burned really bad.
Have you ever been to a glass blowing demonstration with like the furnace? You'll notice that everyone stays back several feet, and the guy is wearing like intense gloves because he doesn't want to get hurt either, because you have to heat it up to so high temperatures.
How high? Like,
Again, I'm not a glass blower. I'm not sure. I'm sorry.
do they literally blow on the glass?
Depending on the type, yes. The reason why they use it, well, they put the little rod on the inside of it, and then they blow that. So that way it's there. It's because again, because the glass is so hot, they don't want to get close to it. So it's a long tube basically, and they spin it as well, so that way it gets a symmetrical shape as they're doing it. Yeah, so look at videos for them. I have a really hard time finding a video that condenses it down and that shows a good quality one, but there are several of them you can find online of glass blowing. Really pretty, really cool. Alright, so that's amorphous cell, so make it over those ones. Crystalline cell, this is characterized by particles in a regular and repeating 3-dimensional pattern. So this would be like ice where it's in that locked in pattern. Now keep in mind, anyone know what temperature does ice start to melt at?
33 degrees Fahrenheit.
33 degrees
32
Fahrenheit?
degrees Fahrenheit.
32 degrees Fahrenheit or 0 degrees Celsius. But keep in mind, that's whenever the ice crystal starts to melt or starts to break apart. Now keep in mind, if I have a lot of grams of ice there, it'll take time for all of them to start to melt. But basically that's its melting point. It'll break apart or not. It's not going to be the slow process for it of it's gradually, like slowly all of it breaking apart. That's the difference between crystalline and amorphous. There's a definite point whenever the bonds have enough energy to break them apart. Alright, any questions about those two? Alright, your book points out with crystal arrangements, we have this simple repeating pattern in a crystal. It's called a unit cell. This has to do with like a 3D object again. That's what your book is trying to show you, but it's hard. One of the easiest ones to talk about is with the cube. That's the reason why we use cubes or dice, is because it's an easier way of looking at it. So this is the simplest of studies that studies a cubic, is the idea of a crystal is made up of basically this pattern over and over and over again. Your book gives an example of salt crystals. Anyone know what shape salt crystals loosely have? You ever looked at them underneath a microscope? You can sometimes see them with a magnifying glass.
Pointy, isn't it?
It is pointy. Do you know what shape?
Is it like
So 3D shape.
a cone?
Not quite. Alright, what else want to guess? It's a square as well for it. So, for those, if you look at them underneath a microscope, they should have this cubic shape to it. So, it has a cubic crystal system. So basically, you have a bunch of them all sticking up on top of each other for it. Now, your book points out it's not quite the same as sticking them just on top of each other. It's a little bit more deep. It's a little bit deeper than that, because the idea of the forces are also holding them all together as well. Your book gives you several examples for them. You don't have to know like all the different shapes. You don't have to know like the different variety in crystal shapes as well. That's the reason why we assume certain shapes or certain patterns with certain gemstones. Is because they typically naturally get these. Now, keep in mind, why is not every diamond that shape then? If that's the naturally occurring one. You still with me, Clinton?
Mm-hmm.
Doesn't look like you.
Never will.
Alright, so why don't we have every diamond look like the diamond in the book?
Because God made it that way.
Nope.
How did make it that way?
Because of different pressures.
Typically no. I guess you could, but typically no. This is more, you might not know this until you're older,
I'm an old boy.
but you'll notice that whenever you're thinking about buying an engagement ring for someone, that there's different cuts or different shapes of the diamond. That's because people on purpose go through and cut them into different patterns and into different shapes. But again, that's because people have decided I'm gonna cut it into a different shape. Or they'll take a large diamond and break it apart.
Getting married.
It's okay, you don't have to. Alright, so keep in mind though that the simplest repeating unit in a crystal is called the unit cell. Your book compares it to wallpaper. Now keep in mind, how many of you have wallpaper in your house? It's a little bit old.
I just have wood in my house, obviously.
You said wood? That's it?
My house is just made out of plywood.
Oh.
I have wallpaper.
So, what is the pattern
No,
of
it's
I don't have a
it's
house.
paint. Is that wallpaper? It's painted?
Technically,
Wallpaper
no.
is paper.
Okay, then no.
Alright, so
I don't have a
wallpaper.
house.
I'm sorry. So, wallpaper is typically the same kind of pattern over and over again, and your parents typically put it up all along a long wall. Make sure you're still keeping your focus, Ethan and Chris. So, this is why the idea was that simplest pattern, a repeating unit. So, your book compares it to a wallpaper pattern. So, if you go over to Grandma's house, Grandma probably has wallpaper in her house, maybe not. But it's the idea of it's that simplest repeating pattern. It's the same idea. It's those simple units over and over again make up the crystal. So, we call those simple units a unit cell. So, make a note for that one. The simplest of the crystals is the cubic crystal system. That's the only one you need to know. So, a cubic is what type of shape? Yeah, so that's easy, that's simple. So take a note for that one. That is the simplest, that is the cubic one for it. I think that is it for that one. Alright, if you look at the top of page 145, your book points out there are several packing systems to try to fit as many atoms as possible into these unit cells for it. Your book points out a simple cubic is like this. So if you put a molecule or an atom at each corner, how many atoms or molecules are in a cube?
12, 16.
You think of something else.
Is it 8?
8, because it's the idea of there's 4 corners at the top, 4 corners at the bottom. So you can fit a total of 8 atoms into this particular shape. Your book points out that is a simple cubic with the idea of one molecule or one atom per corner. There's a couple different other packing ways that you can do this. You could do another one called the body-centered arrangement. That's whenever you take another one and you shove it on the inside of it. So that one would have a total of how many molecules then?
9.
9. Your book points out the last one is the face-centered one, because what do we call this of a dice?
Face.
The face. So that one is, instead of it being dead in the center, it's in the faces between them for it. So the face-centered cubic, this one packs the most atoms into the smallest amount of space. Now it's really hard to see in that picture, so we're gonna watch a lab on it later on, but yeah, it's about 12 for that one for it. So again, not all the time, because sometimes they'll put them on, they'll have another one on the very exact center, but typically it is the idea of there's 8, 8, and then 12. Alright, so we'll go ahead and we'll stop there. Your homework for tonight, read pages 145. Well, technically read back a little bit, because I think your homework goes back a little bit farther. So, so if you have it, so you weren't paying attention, read pages 143 forward, but if you were paying attention, 145 to 147, you'll notice we're about to be done, so 145 to 147. Answer on page 147, questions 1 through 4. So, it's the only question, this is section review at the bottom of the page, so you have to find it. So, 147, questions 1 through 4. You're gonna have your quiz over the shape in that section tomorrow. So if you're stuck on this, you need to come email me or call me or see me in class at study hall tomorrow, and we'll go over the answers tomorrow in class
So
as well.
just 147 and 134?
Yep, that's it.
And we have PE today.
I think so. Oh, okay, that's right. Alright, anyone have any questions? I'll go ahead and stop it for